I hope that you got my email concerning the rest of the semester. Um, the short version is we're going to do everything remotely from now on because so many people told me the past week or so that they're going to do remotely that I don't think it makes sense for us to meet in person anymore because I have to ignore all the remote people while we're in the class. So we're going to do it all remotely. That means everybody will be on the Friday schedule from now on. So our homework and quiz will be due on Friday. It also means we're going to do Zoom on Tuesday and Wednesday and Friday, and everybody can come all of those days. So my plan is on Tuesdays I'm going to do more examples from the section. So today I'm just going to do from 2 out of 3 of the sections. Today I'm going to focus on the graph, the curve sketching with asymptotes, and the or the other one, the Absolute Extrema. And then tomorrow we'll do the Zoom again, and I'll do a little bit of examples about antiderivatives. All right. Are there any questions about that business? No. All right. So let's do another example about curve sketching. So these ones can be a little tricky. I got an easy one and a hard one. So let's start with the easy one then. So the easy one is graph the function minus x over 2x plus 1. This is my function. I'll call that f of x. All right. So first of all, you should look at that and identify, yes, this does have asymptotes, right? You know because it's a fraction and you're going to have an asymptote whenever the denominator is 0, a vertical asymptote. So we got to find the vertical and the horizontal asymptotes. So let's do the vertical first. Vertical tote. And like I said, the way you find the vertical asymptote is when the denominator is 0. So I go 2x plus 1 equals 0 and solve for x. 2x equal negative 1, x equal negative a half, right? And so that's a vertical asymptote. I'm going to start drawing the picture right away. Might as well. Let's say this is minus a half right here. And there is my vertical asymptote. All right. How am I doing so far? Excellent, I assume. What about horizontal asymptote? So for the horizontal asymptote, you have to do lim x goes to infinity minus x over 2x plus 1. This is an old thing. We haven't done this in a long time, but it's coming back. Limit as x goes to infinity. This one, remember, you need to do your you look at the degrees on the top and on the bottom. There was a trick about this. If the degree on the top is bigger, that it does not exist, which means there is no horizontal asymptote. Degree on the bottom is bigger, then the horizontal asymptote is at 0, and if they are equal, as they are in this case, the degrees are equal, you get the ratio of the coefficients. So here we're going to get minus 1 on top and 2 on the bottom. These are the ratios of the x coefficients. So my horizontal asymptote is also at negative a half. I got the same thing here. This is a coincidence. Also at negative a half, I have a horizontal asymptote. There we go. All right, these are my asymptotes. Any questions so far? Okay, so next would be to find the critical numbers and then plot the critical numbers on the graph and fill it and then do the increasing decreasing things. It's the same procedure as last time, it's just the asymptotes make it a little more interesting, and the derivatives tend to be a little bit more difficult. So to find the critical numbers, we use the first derivative. And to find the first derivative, we need to use the quotient rule, right? The original function is a quotient, so when I take the derivative, I'm going to use the quotient rule. And I do it, I go the bottom times the derivative of the top, which would be negative 1, and then minus the top negative x times the derivative of the bottom, which would be 2 over 2x plus 1 squared, like so. Come on now. All right. This is my function. You better simplify because we have to do a bunch more stuff with this. So to simplify on top, let's distribute first. Multiply the negative 1. I get negative 2x minus 2. And then this minus sign will turn that into a plus. So I get plus x times 2. I'll write 2x divided by 2x plus 1 squared as usual. And then up top I have minus 2x and plus 2x in the end. They cancel. And I get just negative 2 divided by 2x plus 1 squared. All right, this is my f prime of x. All right. So let's find the critical number. So that will be where the derivative equals 0 or derivative does not exist. So f prime equals 0 first of all. Negative 2 over 2x plus 1 squared. You set it equal to 0 and solve. You solve by multiplying the denominator over to the other side. And I'm just going to get 0 again, right? It'll be 0 times that denominator. Minus 2 equals 0. What does this mean? This means there are no solutions. So there are no critical numbers from this step when f prime equals 0. There are no points when f prime equals 0. This is going to make the graph slightly weird because usually we plot those points and then connect the dots with the curve, but there will be no points at all to plot. All right, we'll see what happens when we get there. Anyway, we also need to consider when f prime does not exist, dne. That would be when the denominator is 0. So I say 2x plus 1 squared equals 0. And solve this for x. I would square root on both sides. 2x plus 1 equals 0. And then solve for x. I get x equal minus a half. All right. This is my only critical number. And that happens to be where the asymptote is. And actually, this will always happen. If you have an asymptote on the picture, it will automatically appear in your list of places where the derivative does not exist. Okay, let's make our chart with the increasing and decreasing, and then I think we'll be ready to draw the graph. So I'm going to make a little increasing, decreasing, using the first derivative, of course. And the only critical number we have is negative a half, and this is where the derivative does not exist. And so I'm going to plug points in. Point to the left, point to the right of negative a half, and see what the sign is. Actually, in this example, it's easy enough to just look at this. Here, would you agree with me that f prime is always, no matter what the x is always a negative divided by a positive. That's because the top is negative 2, which is negative, and the bottom is something squared, which will always be positive. And so, actually, in this example, the derivative, you don't even have to choose individual points, although you could if you want to. The derivative is always negative. So I'm going to get negatives over here and negatives over here. All right? Always negative in this example. Okay, anyway, let's see if we can graph the function. So back to the graph over here. Now, I have no points at all to plot. This is a little strange. You have to just draw the graph out of nowhere, really. All you have to work with are the asymptotes plus the increasing, decreasing, which in this example is always decreasing. So what you want to do is, let's say, look on the right side of the vertical asymptote. Let's try to draw the picture in over here first. That would correspond to this region of the increasing, decreasing chart. What I want to draw should be decreasing. But if you think about it, there really is not all that many choices that this curve could be. You know, it has to approach the vertical asymptote either going up to infinity or going down to the minus infinity, because that's what asymptotes are. So this curve, it either does that or it does that when it approaches that asymptote. And when it approaches the horizontal asymptote off to the right, it either approaches from below or from above. So it either does that or that as it approaches the asymptote over there. If you put it together, really there are only two choices for what this curve could look like. It either looks like that up there, or it looks like this one down here, right? Those are my only two choices. This is the only way that the curve can approach both asymptotes in an appropriate manner, all right? Which one is it? Which is the true curve? It depends on the increasing, decreasing thing. You look down here, you say this curve is decreasing throughout here. So can one of you guys shout out, which one is it? The one on the top or the bottom? It's got to be decreasing. Sorry, say it again. I heard something. It's the one on the top. Is that what you said? I hope so. It's the one on the top because this is the only one which is decreasing as you go to the right, right? This one would be increasing, so we don't want the bottom one. So I am going to get rid of this one, if I may. It's the one on top here. I'll make it look all pretty. It's this. All right. You use the asymptotes to fit the curve in there nicely. Okay, and what about on the left side of the asymptote? Again, in order to approach the vertical and horizontal asymptotes properly, there's only two options really. This one or this one. And you have to ask yourself, which one is it? And it's based on the increasing, decreasing thing. So in this range, the curve is supposed to be decreasing. That's to the left of -1/2. Between these two, the one on top is increasing, the one on the bottom is decreasing. So we want the one on the bottom. It's this one. All right, and that's it. This is the graph of that function. Any questions about that one? All right, great. So that was an easy one. Let's try one that's a little harder. Did you have a question? Yeah, sure.
Why are we going to do like just no homework? So do you want that afterwards or?
Oh, about like a different problem?
Yeah, because like 19, for example, like it had the graph that goes down and the two that go on the sides.
Yeah, yeah. So actually, the next one that I do is kind of like that.
Okay.
And then if you're still not satisfied, we can talk about whatever specific question. Okay, so let's try, this is a harder one. X squared over x squared minus 6x minus 5. All right. So this one is interesting because it has actually two vertical asymptotes. Let's get it going here. So the vertical asymptote, remember you set the denominator equal to 0. So I go x squared minus 6x minus 5. Sorry, I meant plus 5 down there. Sorry about that. Equals 0. And how do you solve for x here? You should factor. I think in this case I get x minus 5, x minus 1. And then split it up, you get x equal 5, x equal 1. So these here are two vertical asymptotes. I'm going to try and make my picture big over here. Two vertical asymptotes at 5 and 1. So here's 1, 5. One like that, one like that. All right, these are my two vertical asymptotes. Okay, and how about horizontal asymptotes? You do that limit thing, right? Lim x goes to infinity, x squared over x squared minus 6x plus 5. What am I going to get from that? Somebody shouted out.
1 over 1?
Yeah, 1 over 1, I believe. The top and the bottom have the same degree, and the coefficients are 1 each time. So this is 1 over 1, which is 1. Okay, so I have a horizontal asymptote at y equals 1. All right, so this is what my asymptotes look like. Little weird, but it's all right, we can handle it. Okay, let's continue then. The next step would be to find the critical numbers with the goal of plotting them on the graph and then also making the the chart, increasing, decreasing. So let's find the critical numbers. This is going to be a little taxing because this kind of complicated function. We got to do the quotient rule. So I go the bottom, x squared minus 6x plus 5 times derivative of the top would be 2x minus the top, x squared, times derivative of the bottom would be 2x minus 6, right? That's the derivative of the bottom. This is the numerator in the quotient rule, and then I go divided by the bottom squared. X squared minus 6x plus 5, whole thing squared. All right, and as usual, we need to simplify here because we are going to have to find the critical numbers. It's a good idea to simplify. We got to do a lot of distributing. So first of all, I'm going to distribute this 2x like so on these three parts, right? And then I'm also going to distribute the x squared on those two parts. So anyway, distributing the 2x first gives me 2x cubed minus 12x squared plus 10x, right? That's what I get when I multiply 2x times each of those things. And then I go, I'm going to distribute the x squared over those other two things, negative x squared. So it begins with negative 2x cubed and then plus 6x squared. All right. And can we do anything to simplify that? We're going to add all that up in the numerator. It looks like 2x cubed and 2x cubed will cancel, right? 2x cubed minus 2x cubed. Those cancel. The rest does not cancel, but it can add together. Negative 12x squared plus 6x squared gives me negative 6x squared and then plus 10x over this business, x squared minus 6x plus 5 squared. And then finally, just one last thing we can do. You can factor out on top 2x, I think. Let's factor out negative 2x. So what remains here would be 3x and then minus 5. Like that, all right? And this is as simple as this is going to get. So that's a little taxing. I hope I didn't mess any of that up. If you screw this up, it'll ruin the rest of the whole problem. So hopefully that's good. Am I doing all right so far? It's a bunch of simplifying. All right, let's find the critical numbers. Then we got to set this equal to 0 first of all. What do we get from that? Negative 2x, 3x minus 5 divided by some stuff equals 0. The denominator actually doesn't really matter in this case because my first step is immediately to multiply both sides by that denominator, and it goes away. The denominator moves over to the right side where it multiplies by 0, and it goes away. So it's just negative 2x times 3x minus 5 equals 0. And then we split it up and solve as usual. Negative 2x equals 0. 3x minus 5 equals 0. Here I got x equals 0. And here I get x equals, I guess, 5/3, which is a little weird, but I can handle that. 1 1/3 is what that is. 1 2/3, right? That's what 5/3 is. Okay? So these are two critical numbers. And then we also have numbers where the f prime does not exist. Let's try it in. That would just be setting the bottom equal to 0 as usual. I'm using the bottom from f prime of x, remember? And then what do we get from this? You can get rid of the squaring by square rooting on both sides. I get this. And then actually this you solve in the same way. It factors, just like we did to find the vertical asymptote. The factors are x minus 5, x minus 1. And we get x equal 5 and 1. So these are 2 points where the derivative does not exist. All right. Overall, I have 4 critical numbers, don't I? 2 where the derivative is 0, 2 where the derivative does not exist. Let's make that increasing and decreasing chart. I'll do it up here because it's not very convenient, is it? I'll do it over here. I want to be able to see everything at once. All right, increasing, decreasing. I have 4 numbers to put on the chart. They are 0, 5/3, 5, and 1. So in order 0, 1, 5/3 is more than 1, right? And then 5. All right, and these points are ones, this one, the derivative is 0. Here it does not exist. Here it's 0 again, and in here it does not exist again. Okay, and we are going to plug in values in various regions. So all the way to the left, I'm going to use x equal -1, f prime of -1, plugging into the formula that you see in the box right there. It's -2 times -1 times 3 times -1 minus 5 divided by. In this example, I'm just going to say over something positive. The bottom, I will have you notice, is something squared. That means the bottom will always be positive no matter what. So we don't even have to worry about plugging into the bottom. Whatever it is on the bottom, it's always positive. So what is this then? Of these three factors on the top, one is negative, and then times a negative, and then I got 3 times -1 minus 5, that's -3 minus 5, which is negative. All of that divided by positive, that gives me negative overall. So in the first interval, the leftmost interval, it is decreasing. All right, next, in between 0 and 1, I guess I have to use 0.5. So plug that in, -2 times 0.5 times 3 times 0.5 minus 5 divided by something positive. This is negative, positive, and that's still negative, right? 3 times 0.5, that'd be 1.5, minus 5 is negative, divided by a positive. This ends up being positive, so I get a positive in that region. All right, keep going. Plug in the next point. Between 1 and 5/3, 5/3 is 1 and 2/3, so I'm going to use 1.5 for that one. -2 times 1.5 times 3 times 1.5 minus 5 over a positive. This is negative, positive. 3 times 1.5 is 4.5. Minus 5 is negative, so that's negative right there over positive. This is positive, so it's positive right there. All right. And then between 5/3 and 5, let's use 2. 2 is more than 5/3, right? I get -2 times 2 times 3 times 2 minus 5 over positive. This is negative, positive, positive over positive. This is negative, negative right there. And then finally, to the right of 5, let's use 6. F prime of 6 is -2 times 6 times 3 times 6 minus 5 over positive. This is negative times positive again over positive. This is negative again. All right, that's my whole chart of the positives and negatives. Almost ready to draw the graph. The only thing that remains is we need to find y values for the critical numbers, which I intend to put on the graph. Those would be these ones where it's 0. So y values for x equals 0 and x equal 5/3. I'm not trying to find a y value for these DNEs because those ones are right on the asymptotes. So there is no y value for those ones. But the other two, there should be y values, which we can find and plot on the graph. So remember, for the y values, you use the original function, which is way up here. X squared over, I will just copy it down here. I'm using f of x equal x squared over x squared minus 6x plus 5, right? And I'm plugging in 0 and then 5/3. So when I plug in 0, that's easy enough. F of 0 is 0 squared over 0 squared minus 6 times 0 plus 5. This is 0 divided by 5, which is 0. So I get x equals 0, y equals 0 is one of my critical numbers that I can put on the chart. Let's put it on the graph immediately, if I can. So it was 0, 0 right there. All right. This is a critical number. So just to remind myself, this is where the derivative will be horizontal when it goes through that point. All right. And my other point was 5/3. Now this is going to be a bit of a pain to plug into the function, but it's f of 5/3. What's that going to be? 5/3 squared divided by 5/3 squared minus 6 times 5/3 plus 5. And this, unfortunately, I'm going to have to use my calculator. I hope you don't mind. Like I always say, ordinarily, you know, on a test or a quiz, I would make it so that the numbers all work out nicely. So I'm going to multiply this out. So instead of 5/3, I'm going to use 1.66. It's rounded off. In the numerator, I get 2.75. It's actually 2.755. And then on the bottom, I get that same number, and then minus 6 times 5/3 would be 10, right? And then plus 5. Negative 2.244. So dividing 2.755 divided by negative, oops, no, I typed it in wrong. I don't use my calculator very often, so come on, man. 2.755 divided by 2.244. I'm not a calculator master here. I get 1.22. Anybody agree with me? Maybe, I don't know. This is the y value when x is 5/3, 1.22. So on the graph, 5/3 would be 1 2/3, which is around, like around here, right? And then the y value is 1.2, which would put it slightly above the asymptote. Because that horizontal asymptote is at 1, right? This is 1 here. This is 1, 2, 3, 4, 5. Okay? And this also is a critical number, so the graph should be flat horizontal when it passes through that point. All right? We got our 2 points on the graph. Okay, what remains is just to draw in the curves, and the curves have to respect the asymptotes, and they also have to go through those 2 points appropriately and obey the increasing, decreasing. This is the important thing about this example. So I will just so we can see it all at once, I'm going to copy that increasing, decreasing thing. We had 0, 1, 5/3, and then 5 were our special numbers. And I believe, I don't remember, minus, plus, plus, minus, minus. All right. Minus, plus, plus, minus, minus. Okay? So let's see if we can fill in the curves appropriately. Let's look first of all to the right of the rightmost asymptote. In this case, we just need a curve which fits both the vertical and the horizontal asymptotes. And just like before, there are 2 options, really. It could do that or that. And which one is it? Depends on the increasing, decreasing. And when I look at the chart, I see it's decreasing, which means it should be the one up top, not the one on the bottom, because that is decreasing. So I'm going to draw it in red just because I like the look of that. All right, that's what the curve looks like to the right of 5. All right.
Wait, so the top doesn't, that's not increasing, that's decreasing?
That is decreasing, yes. Remember, you always judge looking from left to right. Does it go down or up? And looking from left to right, it goes down. Yeah, it can be confusing. All right. What about between 5/3 and 5? You know, from that point in the middle there, going to the right, if you approach the asymptote, it either has to look like that or like that. And which one is it? It's the one which is decreasing, which is the second one I drew. It's the one down below. So from this point heading to the right, it goes down like that. All right. Remember, it should come out of that point in a horizontal fashion and then go down because it's decreasing. Okay, you may be concerned that the line actually went through the horizontal asymptote. That actually is possible. seems a little weird, but that can happen. The asymptote doesn't mean that the curve can't go through that that dotted line. It means that as the curve goes out to the right or to the left forever, it approaches close to the dotted line. But it can go through if I mean, sometimes it has to. The vertical asymptotes, on the other hand, you cannot go through them because the function does not exist along the asymptote, along the vertical asymptote. Anyway, what about in between 1 and 5/3? That would be from this point, but on this side of it. Again, we have a vertical asymptote, so there are only two options. It could go down like this, approaching the asymptote, or it could go up like that, approaching the asymptote. According to the chart, the function should be increasing in that region. And remember, this increasing, this means as you move from left to right, the function goes up. So which of those two blue lines is it? It's the one on the bottom. That's the increasing one. Oops. As you move to the right, the function comes up, like so. All right. Okay, we're getting there. Almost done, maybe. How about between 0 and 1 in this region, right? The chart says increasing here. That means the curve along this right around here, it leaves this point 0. And does it go up or down as it approaches the asymptote? It must go up because the curve is supposed to be increasing. So from there, it looks like this. And then finally, the leftmost side of this picture, over here, right? The curve decreases down to this point, and as we go out to the left, it has to approach the asymptote. The only way to make that happen is like this, decreasing down to that point, but it has to approach the asymptote. All right, that's my curve. A little strange looking. I think this is correct though. You can always graph this on your calculator or something to see if you did it right. Any questions about that one? This is a hard one. And this one I would not put on the quiz, but really only the part when I had to plug that weird number in and got the weird answer on my calculator. Otherwise, well, it's probably too long to put on a quiz, but otherwise, you know, this is not unreasonably hard, but it is kind of hard. Does this address your questions from before, Matt, or did you have something else?
No, it makes sense now.
Okay.
When I saw you writing them on the chart and then how you agreed that makes sense.
All right, great.
That's what I was.
Okay.
Thank you.
All right. If there are no more questions about that, I wanted to do one quick example of the Absolute Extrema, which was the other topic. Well, there were 3 topics for this week, but I wanted to do 2 today and 1 tomorrow. So, Absolute Extrema. Let's try one of them. These are much easier. Find the Absolute Extrema. They're easier than Relative Extrema even. Absolute Extrema for f of x equals x squared minus 3x plus 2 on the interval 0 to 3. All right. Remember, what absolute extrema means is the absolute highest and lowest points on the graph. There is always going to be one absolute maximum and one absolute minimum. If you restrict yourself to a closed interval, so this function looks like something, and the interval is from 0 to 3, it means if I look only along these points, which on this picture will be only along these points of the graph, which one is the absolute highest and the absolute lowest? In this example, this would be the absolute minimum, and this would be the absolute maximum. Sorry, it's behind my beautiful face. All right. On that, I just made up that picture though. That's not what this this problem is. Not about this picture. The problem is about this function here. The idea is we find the critical numbers and then plug them in to f to find the y values, along with the interval endpoints. Right? Because as you can see in that picture that I drew there, sometimes the absolute maximum and minimum occur at one of the critical numbers, like this one is at sort of this critical number there. But also sometimes they just occur on the ends of the interval. And so you need to check the critical numbers and also the ends of the interval to see where the absolute extrema lie. All right, let's do it. In this example, I'm going to find the critical numbers first. We take the derivative. In this case, it's just 2x minus 3. We set this equal to 0 and solve, so I get 2x minus 3 equals 0. Solve for x. Come on. 2x equals 3, x equals 3/2, also known as 1.5. All right, and then f prime does not exist. This never happens in this example because I don't have any denominator or anything. That's the only time when the derivative would fail to exist. All right. Okay, now we make, I'm going to just make a little chart of x values and y values. What do we need to check? We need to plug in the y values for critical numbers and along with the interval endpoints. So I'm going to make a little chart here, x and y. My critical number, there's only one of them, it's 1.5. And my interval endpoints were 0 and 3. This I gave you at the very beginning of the problem. And then we just need to plug each of those values into the function. The original function, make sure you don't get yourself confused. Don't plug into the derivative in this step, plug into the original function f of x. So for the first one, I do f of 1.5. This would be using the original function up here. F of 1.5, that's 1.5 squared minus 3 times 1.5 plus 2. Can I use my calculator for that too? I don't know what 1.5 squared is. 1.5, 2.25. And then I go minus 4.5, and then I go plus 2. Negative 0.25. All right, so that goes in my chart right here. The y value there is negative 0.25. All right. What about 0 and 3? I plug in 0. This I can do this without my calculator. F of 0 is 0 squared minus 3 times 0 plus 2. That is 2. All right. And then 3, I can do this on my brain. I don't need my calculator for that, I think. 3 squared minus 3 times 3 plus 2. This is also 2, isn't it? 3 squared is 9. 3 times 3 is 9. So I get 9 minus 9 plus 2 is 2. So this is 2. Did I say there's always only one maximum and only one minimum? This is true as far as the y values go. So my answer is negative 0.25. Well, let me say, so I'm just going to say the absolute minimum is you choose the smallest of those y values. The absolute minimum is at x equals 1.5, y equals negative 2.5. Sorry, it's 0.25. 0.25. And then the maximum would be those other ones. By coincidence, I got the same answer 2 different times. This can happen. It doesn't usually happen, but I will say the absolute maximum is at x equals 0 or 3, and the y value is 2. All right, this is the absolute minimum and the absolute maximum. So that's how we do the absolute extrema. The absolute extrema are easier than many of the other things that we've been doing lately. In my opinion, you don't have to do as much work for it. And that's about all that I had prepared to go through. Any of you guys have any questions about those particular ones, or ones other ones that you've been looking at on the homework?
I'm good for now.
All right. Well, if there are no questions, I think we've got 7 minutes on the clock, but I think I'm ready to call it a day in that case. I will be in my office hours from now until 2 anyway, so if you do have more questions, feel free to hang around. Oh, yeah.
Administrative question.
Okay, sure.
How are the quizzes going to be like now? Like, are we still going to use Gradescope, or like, how are we going to do that now that we're all
Yeah.
online?
Yeah, so all of our quizzes will be on Fridays from now on, and you should just come, like, on Friday. We'll have the Zoom. I won't have anything prepared to say, but I will, try as best I can to sort of talk to everybody like I usually would during class. And then at the usual time, like 15 minutes before the end, we'll do the quiz, and I will just write the quiz on the screen. You write your own answers on your own paper and then submit it to Gradescope the usual way. That makes sense?
Okay, thank you.
Yeah. All right, then I will see you back here tomorrow. For those of you not familiar with the Wednesday schedule, class on Wednesday is starts at 1 rather than 12:30. So class on Wednesday is at 1. Class on Tuesday and Friday is at 12:30. All right. See you then.
Thank you.